Today I will discuss on dynamic programming problem. In practical decision making situations, decisions have to be taken in different sequentially in different points, maybe points in time, points in space, rather for different subsystems. Now, dynamic programming is an optimization tool that transforms a complex problem into sequence of simpler sub problems, so that we can solve the sub problems and we will get the optimal solutions of the sub problems sequentially to get the optimal solution for the original problem. Now, since the decisions are being taken at different points in time or in spaces, that is why we are taking decision in different stages. Thus, the dynamic programming problem is also being named as the multi-stage decision making problem. The basic philosophy of for solving a dynamic programming is that the first step is that define the decision situation into smaller parts. Rather, we have to decompose the whole problem into smaller parts, and for each part we have to take a decision. This is the basic approach for dynamic programming. Now, we will take a small part of it and we will take the optimal solution for the small part. Since we have considered a subset of the whole problem, now we have taken the optimal decision for the smaller part, then we have to enlarge the small part, the small problem, by considering optimal solution of the previous problem we have to consider the information about the current state rather, current enlarged problem. Then we have to take a decision of this enlarged problem, and we will repeat the process. We will repeat the process means we have started from a smaller part, we have enlarged it a little bit, then we have to enlarge further. How the enlargement is being done, how the smaller problem will be converted to a bigger problem, that I will show you with the example in the next, and that is the technique for solving with the dynamic programming methodology. Enlarge further as long as the original problem is being addressed fully. And we have to take the optimal decision of the last bigger problem, and once the optimality reach, then we have to trace back the subsequent stages. To get the optimal solution as a whole. Now, if we see the whole process, the beauty of this process is that the big problem has been divided into smaller parts. That means, we have decomposed the whole problem in different stages. That is why we are sequentially reaching from stage 1 to stage n, so that at stage n we are fully addressing the whole problem, and whatever optimal solution we are getting at the end, and each step we have to apply the optimization technique, and that would be the optimal solution of the problem. Now, this methodology, this dynamic programming concept has been invented in 1950s by American mathematician Richard Bellman. And dynamic is the decision, since we are taking decisions in several stages, that is why it is dynamic, and programming stands for the planning or to just set the action in the best possible way. And if you see the whole process, you could realize that the process, we are repeating the optimization technique again and again for further enlarged problem. That is why this is a recursive process we are adopting. That is why in other way also we can say the dynamic programming as a recursive optimization. Thus, we can name the dynamic programming as either multi-stage optimization process or recursive optimization problem. Now, the process as a whole I described to you, there are few things to be discussed, that how the problem can be divided into smaller parts, rather how the problem can be divided into smaller stages, and how to reach the optimal stage. These are the basic understanding for dynamic programming problem. That is why let us start, before going to the detail of dynamic programming technique, let us take a simple example. There are several applications of dynamic programming problem. One of the most popular application is the shortest path problem. We are applying the dynamic programming technique. In the knapsack optimization problem also we are applying the dynamic programming technique. Otherwise, we are also using for inventory management problems as well. Let us take a small knapsack problem for further discussion about the methodology of the dynamic programming problem. This is an optimization problem. Let me write down the statement of this problem first. A young lady is on her trekking way. She is trying to fix. She is having a knapsack, and there is a specific volume of that knapsack. Accordingly, she is planning she wanted to carry food pack, she wanted to carry water bottles as well as tent for her troop. That is why let me just put the situation in this way. She can carry at the most in her knapsack, she can carry at the most 10 kgs. We wanted to utilize the whole space of her knapsack, but there are certain constraints, certain information related to the things which she is trying to pack up. Three possible items with their utility values are given. Utility values are something, these are being utility values are given, that is from her experience she gathered the values. This is certainly subjective in nature, and the utility values. The first item is the food pack. Unit food pack is having the weight 3 and the utility value 7, 2. That is the bottle of water. Individual bottle of water is having the weight 4 kg and the utility value is 8. And if she wanted to carry the tent with her, the unit tent is having the weight 6 kg and the utility value is 11. This is the only information is given to us. Now, we have to suggest to the young lady how she can plan so that 10 kg will be utilized fully. Not only that, she can maximize her satisfaction level. That means, we wanted to maximize the utility value for this problem. If we see from the given information, we can see that if I just consider the ratio utility value divided by weight, what we can see, these values are for the food pack 7 by 3, that means 2.33. Similarly, for the bottle of water it is 2, and for the tent it is coming 11 by 6, 1.83. That is for tent. As we could see that food pack is having better utility value, unit utility value, that thus we can suggest in an ad hoc way that you just consider the food pack as many as you can, but if we see the data set, it is having the weight 3 kgs, that is why she can carry at the most 3 food packs, but 1 kg will not be utilized. That is why the whole constraint will be underutilized in this case. Thus, whatever decision we are giving, that pack 3 food packs, that is not the very good way, wise way to suggest. That is why we have to take a decision in a scientific way. That is why the optimization techniques are available with us, and there is one way for solving this, that is the integer programming problem. We can very nicely just construct the integer programming problem in this way. If we consider x1 is the number of food packs for number of food packs, x2 number of bottle of water, and x3 is the variable for the number of tents, then we can find out the maximization of the total utility value 7x1 plus 8x2 plus 11x3, and there is a constraint subject to that is the total weight must be lesser than 10. And here we need to consider x1 and x2 and x3, these are all the integer values. We can solve it with a technique you have learned, the branch bound technique, or in other technique of integer programming we can solve it, but we do not want to do it. We want to apply the dynamic programming technique for solving this problem. And as I said, this is though it is a simple problem for us, but since we are doing it manually, we can consider as a larger problem. We will break the problem into the smaller problems. That is why we will break the problem into multi stages and we will solve the problem. How we can divide the situation in different stages? One possibility could be, first we will decide that if I want to utilize 10 kgs of weight, then first let us start from the back. We will first select how many number of tents we will consider. That could be the first stage. Second stage could be the how many tents as well as the number of bottle of water we will consider together. Alright, that would be the second stage. And the third stage is the tent, number of bottles of water and the food packs. In that way we can divide in 3 stages. Thus, we can say that our stage 1, stage 3, let me start with stage 3. That is the number of tents, stage 2, number of tents plus bottles of water, and stage 1, that is the bigger problem for me that we wanted to address, that is the number of tents plus bottles plus food pack. There is a constraint that total weight must be equal to 10 kgs we wanted to utilize. If we just proceed in this way, then this process is being named formally in dynamic programming problem as a backward recursive process, because we are starting from stage 3, then stage 2, then stage 1, we are considering the whole. We can do the reverse way as well. We can consider the number of food packs first, then the number of food packs plus bottles, then number of food packs plus bottles plus number of tents. In that way also we can consider. Now, these are the different stages we have considered. Now, let us see, once we are considering the stage 3, what is happening in stage 3. If we consider a variable as D3 about the decision regarding the weight, in stage 3 we have considered only the tent. That is why the decision about the weight of the tent can be from 0 to 10, any value. Thus, let me consider D3 as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all right. And if we see the situation, we can associate another variable, say x3. x3 is the number of tents we wanted to suggest. This could be either 0 or 1, because as we know the tent weight is 6 kg, that is why either x3 can be 0 or x3 can be 1. There is no other possibility for this. If this is so, let us write down the utility values for the entire situation. For 0, 0, if the number of tent 0, then total weight 0. Number of tent 1, total weight is 0. That is impossible, infeasible solution. That is why let me put a dash here. Number of tent 0, but total weight 1. These are all the possible, but if I just move 0, 1, 2, 3, 4, 5, if I move to 6, then what is the value for x3 is equal to 0? That is 0. But if I consider that we are suggesting one tent for her, then D3 is 6 kg, that means decision regarding the weight in the knapsack, if it is 6 kgs, then what is the utility value? Utility value is 11 here. Now, go to the next 7, this is 0, the utility value is 11 again. This is the simplest situation, and let me just complete the whole table in this way, 11 and 11 here, and all other coming infeasible solution. If this is the case, there are only one option in each case, but it is not happening for other stages, because once we are moving to the further stages, we will see that situation will be much more complicated. In that case, we have to select the higher utility value, that is our objective. Thus, we can say that F3 is the objective in the stage 3, which is the maximization of the utility value. If we just write in this way, otherwise we can write mathematically maximize utility value is 11 x3, x3 could be either 0 or 1. Mathematically we can write it, then we can see the utility values are coming this way, 11, 11. This is simple situation, that is for stage 3. Let us move to the next stage, that is stage 2. What is happening, just see. Here also we are considering D2 as the decision regarding the weight of tent as well as bottle, total weight. Already we have considered the weights for tent as D3, and what about weights of bottles? If I consider x2 is the variable regarding the number of bottles we wanted to consider, then D2 must be is equal to D3 plus 4 x2, because 4 is the unit weight for bottle of water if this is so, and then D2 is the variable, and there is a name for this D2 variable. I will just name it formally later on. I will tell that for each stage there is a set of state values, there is associated state variable, that part I will discuss later on. We can see that D2 is equal to D3 plus 4 x2, and what else we can say? Since the weight of the bottle is 4 kg, then either we can consider x2 equal to 0 or 1 or 2 at the most, not more than that. Alright. Let me complete the table as we did for the other set. X2 is equal to 0, x2 equal to 1 and x2 equal to 2, and we will write down the utility value for each and every cases. Here also the same, D2 can be from 0 to 10. If D2 is 0, then this is 0. If D2 is 1, 0, D2 is 2, 3. But once it is coming to the weight D2 equal to 4, that means we are considering one set of bottle. We cannot consider the tent here, D3 is 0 rather here. Then what should be the utility value? Just now we have considered in the table that the utility value of the bottle of water is 8. Thus, we can say for this is 0, this is 8. Okay. Let me consider 5. If it is 5, again there is only one possibility, x2 must be is equal to 1. There is no other possibility. If I consider 6, then there is a possibility that it could be 1 tent, that is why the utility value is 11. We can consider as well 1 bottle even. Still the knapsack is underutilized. Still we may consider, because we wanted to see each and every alternatives for these different decisions. Alright. If it is 7, here also the same situation. But once it is coming to 8, either we can consider 1 tent or we can consider 1 bottle. We may consider 2 bottles as well. That is quite possible, because total kg is 8 kg and our maximum limit is 10. Therefore, it is quite possible for 8 we can have all 3 alternatives, and if it is 9 we can consider 1 tent, or we can consider 1 bottle of water, or we can consider again 2 bottles of water. Alright. If it is 10, the beauty here comes. We can consider 1 tent, x2 equal to 0, x2 equal to 1, that means we are considering 1 bottle, but there is a provision to have 1 tent as well, because 1 tent 1 bottle will be total will 10 kg. That is why what is the total utility value here? 11 plus 8, that would be 19 here, and here if we consider 2 bottles there is no space for tent, that is why 16. Let us see the utility values for the individual cases. When D2 equal to 0, the utility value is 0. If I just move in this way up to 3, this is 0, up for 4 it is 8, again for 6 it is 11, for 7 it is 11, for 8 maximum value is 16, this is for 8, this is for 9 the maximum value is 16, but see for 10 the maximum value is 19. Thus, if we without knowing even the much complicated dynamic programming technique, here also we can decide that that could be the optimal solution up to this stage. If I consider this problem as individual optimization problem, then we can say that this is the optimal solution. And here you see we have just considered the value of the previous stage and utility value and the utility value of this stage without considering further else. If I go to say stage 1, just see what is happening. That is why this is the optimal solution for stage 2. Let us go to stage 3, and also we can say many things here. Just see, we can develop a relationship. We can say that F2 D2 equal to maximization of 4x2, all right, plus F3 D3 clear, and over x2 could be 0 or 1 or 2, maximum value is coming 8, plus F3 D3 just now we have calculated that was 11. That is why we can say that this could be the relationship between the previous utility value and previous objective function, previous stage objective function and the current stage objective function. Here we will see later on that we can develop a nice result from here. We can write down the result as f for the backward recursive relation Fn minus 1 Dn minus 1. What is your D2? D2 is in this stage, D2 can take any value, D2 is the decision we wanted to take. It could be 0, it could be 10 even, it could be in between any value. Thus, here also if we consider the n minus 1th stage for a general problem, we will see that that would be maximization of, this is the notation, let me use it now. I will describe later on what is the meaning of R n minus 1 Dn minus 1. This means that immediate return we are getting after selecting Dn minus 1. If I see here for D2 is equal to 9, D2 equal to 9, what is the immediate return? Immediate return for x2 equal to 1, that is 8 for us. That is why we have considered in this way, plus f and dn. You can understand this relation later on. This is a very important relation in our dynamic programming technique. I will discuss later on this one. At least we can say that the objective functional value is optimal objective functional value of the next stage is very much dependent on the objective functional value of the previous stage. Thus, I said, if you remember, I just started my lecture with that thing that we have to first take a smaller part of a problem, then we have to enlarge the problem little bit by considering the optimal value of the previous problem, and we have to consider the return values, rather the information regarding the decision at this stage in detail, and both considering together we have to take the optimal decision for the next stage, and we have to proceed further and further as long as we can address the whole problem totally. Now, let us move to the next stage, that is stage 3. Stage 3 means what? We wanted to consider tents, we wanted to consider as well as the number of bottles of water as well as the number of foot packs. Oh, this is stage 1. I started with stage 3. The naming convention is up to the person, up to the decision maker. That is why I can say that D1, that is the number of, that is the capacity, that is the total weight in this state, is D1. If it is so, this must be is equal to the weight of coming from the previous stage plus weight of the current stage. That weight is 3x1, because if I consider x1 number of foot packs, then total weight would be 3x1, and D2 is the weight, optimal weight. Just now I have considered from the previous stage, that is for tents as well as for bottles. If this is the case, we wanted that D1 must be 10, because considering D1, considering we have fully, now we are fully addressing the whole problem. That is why it is not better to consider D1 as 10. If we consider D1 starting from 0, 1, 2, 3, 4, 5, that is not very much good way to think it. That is why better to consider D1 as the, we wanted to utilize the full space, that is why D1 is 10 here. Now, once d1 is 10, then what about the value for x1? x1 kgs are 3 kg individual in unit kg, that is why x1 could be 0, x1 could be 1, x1 could be 2 and x1 could be 3 even, because if I consider number of foot packs 3, at the most it would be 9 kgs. Okay. Now, we wanted to utilize, let us see the whole situation in this stage. If we consider x1 equal to 0, what does it mean? x1 equal to 0 means from here d1 is equal to, rather d2, let me consider d2, d2 is equal to d1 minus 0, that is equal to 10 only. If I go back to 10, the previous stage, if d2 is equal to 10, the corresponding objective functional value is 19 and here the return is 0 for this case, that is why 0 plus 19, it would be 19 only, alright. If we consider x1 is equal to 1, it means that d2 must be is equal to d1 minus 3, that means 10 minus 3, that equal to 7. Go back to the previous table. For the 7, the corresponding value, objective functional value is 11. If I just substitute here, the return from this state, we have considered 1, that is why return will come as 6, no 11, the 7. If I consider 1 foot pack, the return is 7 and here the return is, for 7 the return is 11, that is why we will consider 7 plus 11, that is equal to 18. Thus, this is 18. Let us consider x2 equal to 2, which means d2 is equal to d1 minus 6, that means 10 minus 6, that is equal to 4. Go back to the previous table. The 4, the corresponding utility value, optimal utility value is coming 8. That is why if I go to the formula, fn minus 1 dn minus 1 is equal to maximization of r n minus 1 d n minus 1 plus f and dn. Just now we have considered f and dn is equal to 8, and what about r n minus 1 dn minus 1? We are considering 2 foot packs, that is why total utility value will be 14. It is coming 14 plus from here 8, that is coming 22. Clear? If I consider x1, why I have written x2, this is x1, x1 equal to, if it is 3, then certainly d2 must be equal to 0, d2 must be not 0, d2 must be is equal to 1, that means we cannot consider any taint at all, the corresponding value is 0, that is why the utility value is coming only for 3 foot packs, that is coming 3 into 7, 21. If we just see this stage, there is something to be decided that the maximum utility value is coming for this option only, that is why this is the optimal solution for us. And if I consider f1 d1, that would be is equal to 22 here, and this is the one thing, and here we can conclude that how many foot packs etc., how many items we will consider one by one. For this case, if I go back to this case, what we have seen? We have seen that x1 equal to 2 and corresponding d2 equal to 4. Go back to the previous page, d2 equal to 4 means we have considered x2 equal to 1, alright, and we have considered x3 is equal to 0. That is the optimal decision, and I just explained the process in detail because just we wanted to say few things up to this, that in every stage, if I just concentrate on this stage, the last stage, in every stage the optimal objective functional value is dependent on the optimal objective functional value in the previous stage. Without looking at that, how we have reached to that position, that is very important for dynamic programming technique. Thus, the Bellman, when he invented this methodology, and there is a principle of optimality by Bellman, and it has been clearly said that very nice optimality theory. I will just formally introduce that part right now. The characteristics of dynamic programming. Since the problem I have explained, hopefully it is clear to all of you how we have considered the stages, etc. That is why for applying the dynamic programming technique, first thing is that we have to consider the stage. We have to decompose the whole problem into smaller parts, that is called the stage, and this is the essential feature of dynamic programming problem. And stages are being computed, we have to get the optimal solutions of individual stages sequentially. Now, the stage can be dependent on time, it may not dependent on time, and the problem I just considered there is no dependence on time, but if I consider a simple example, that is for the inventory problem. We wanted to take decision that about the quantity to be ordered in every month. That means the decisions are being dependent on very much on time. If we are in, we have a data set from there, from the experience we just wanted to decide that in which month how much to order. For that thing we need few information with us. It is given that inventory level in each month, we have the order amount in each month. Not only that, we have the demand rate as well in each month. From there we have to take the decision how much to order in each month. This is the data for the previous year it could be. Now, I just wanted to say that the bigger inventory problem can be subdivided into smaller problems by considering in each month there is a small optimization problem as if we have. Once we are defining the stage, the next critical part is to define the state. Generally stage is being termed as n. N can start from the n to 0 or we can start from 0 to n. Depending on that, we, as I have just now developed the backward relationship from stage 3 to stage 1, similarly we can go from stage 1 to stage 3 and we can develop the forward recursive relation for the problem. That is the thing about. Now, regarding the state, for each stage there is a state. Since we have different states in states, that is why we will just we will just associate some state variable. For the previous problem, state variable could be, for stage 2 it was x2, for stage 3 it was x3, like that. Thus, we can have different values for different state, for individual state variables. These correspond to the different states, and there is no state rule how we will define the state. As we have considered the state variables, like by considering the stages with first tent, then tent plus bottle of water, then the tent plus bottle of water plus foot pack. Instead of that, one may consider tent, bottle of water and foot pack in individual stages, etc. That is also quite possible. There is no set rule. From the experience you have to do it. That is why it is very critical to find out the states. Generally states we are just writing with the variable Sn. There we have written xn in the previous problem. There is another part is there. There is a decision variable, as we have done there d1, d2, d3, these are the decision variable. There is a set of possible values of the decision variables. That means there is a domain of decision variable, and that domain is being named. If I consider decision variable as dn, Domain may be considered as capital Dn, Dn is the decision space, and regarding the decision space, it could be discrete, it could be continuous. That is why once you are learning the dynamic programming technique, you have to know the detail of the discrete decision space how to handle, as well as the continuous decision space how to handle. That both the things you have to learn together. That is why it could be discrete, it could be continuous. And second very important thing is that is called the stage transformation equation, or transformation equation also it says, and this equation tells you that how one state of the previous stage is being transformed to the next state of the next stage. That means, one state in stage n, how it is being converted to the next state of stage n minus 1. Who is responsible? This stage transformation equation is responsible. For example, as I have taken the inventory problem, in the inventory problem I can consider, if I consider the inventory level as at nth stage, this is very much dependent on the inventory level of the previous state plus ordered in the previous month minus demand, that is the consumption in the previous month, if I consider it as a R. If this is so, this is the stage transformation equation for the inventory problem, all right, because as you could see that In is function of In minus 1, that is the beauty of it. Now, this is the next part. Now, if I just draw the figure of a multi-stage decision making process, then we would see that state Sn and the decision Dn these are the inputs for stage n. Then we will have the stage transformation equation Sn Dn, and we will move to the next state, that is Sn minus 1. That means, we will move to the next stage where we have different states, stage n minus 1, all right. And if these are the inputs, we are moving to the next. There is a, for individual, as we have seen for individual stages, we have considered the optimal return value. That is why we may consider the optimal return value as Rn. This is again the function of Dn and Sn, all right. Here also the stage transformation equation is there. For each stage we have the stage transformation equation, and we have the, again we have the optimal return in each stage, and in this way we will just move to the next state or next stage again and again to reach to the whole problem. And if I just write in a mathematical rotation this fact, whatever I have done in this figure, the same thing if I just want to write in mathematical rotation, that then we have to write down that is the decision, that is the objective functional value in the nth stage is equal to maximization of return of individual stages plus, if I consider this stage, here is a input decision about Dn minus 1. Then at this stage, if I want to consider the decision, this is dependent on the return of this value plus the return of the previous one. In this way, we will just proceed to R1 D1 S1, where we have considered the stages as the through the stage transformation equation, because as we have seen this Tm function is responsible for this, where m is running between 2 to n, because if I consider it is n minus 1, Sn minus 1 is the function we are getting Tn Dn Sn in this way, and it will end to m equal to 2, then only we will reach to the last stage S1, and it is coming from then the 3, all right. And here the decisions are in the decision space. I just wanted to write down in a mathematical way this thing. In other way also we can write it, just see, you will get the, you have seen the same pattern previously, that f n d n is equal to maximize r n d n, we can write S n as well. And if I just consider the whole part from here to here, this is the f n minus 1 d n minus 1. Thus, the nth stage value is dependent on the n minus 1th stage for the forward recursive relation. In the backward recursive relation, the situation is totally different. From here, the next, the formal statement of optimality has been reached, and let me write down that optimal Bellman's principle of optimality. If I write down formally the Bellman's principle of optimality, it says that an optimal policy has the property that whatever the initial state is, I have just copying the Bellman's principle of optimality, because that is very important. You shall have to learn the thing in a formal way. I will explain it further. Constitute, and the remaining decision must constitute an optimal policy with regard to the state first decision. Now, what is the meaning of it? It means that for a sequence of decision in multi-stage optimization problem, in dynamic programming problem, regardless the current decision d n and the current state s n, all the subsequent decisions must be optimal. Now, the problem we have solved before, you must have seen that if I am in one stage, nth stage, I am just using the optimal solution of the previous stage, and how we have reached to that point, that is not more important for us. Only important is that up to reaching that point, what is the optimal value, and according to that we have taken the decision. That has been said in the Bellman's principle of optimality. That is very important. And if we just see that is the shortest path problem, there we will see that if I just see the shortest path, you know the definition of a shortest path problem, and I will just explain the thing in a better way in the next. And we will see that if I consider a particular stage, at that stage, it is not important for me how we have reached to that stage from the initial point. It is more important for me in the previous stage, what was the optimal value, how much distance I have covered, how much minimum distance I have covered, how much minimum cost I had to incur for it. That information only needed, because that was the optimal solution of the previous stage. That is why how we have reached to that state, that is not important for taking decision at the current state. That is the Bellman's principle of optimality, and that can be very nicely explained with the shortest path problem. Just look at the shortest path problem. This is the problem. We have to move from vertex A to vertex B, and there are different paths in between, different cities are there. We want to travel from city 1 to city 10 say. These are the different alternatives in front of us. We have to take a decision that in which way shall we move, so that the total cost is minimum. And for travelling from one node to the other node, the individual costs are given with the green color pen, and we have to take the decision accordingly. How shall we approach for this? For approaching to this problem, first of all we have to divide the whole problem into different parts. That is why we have to divide the problem into different stages. We can go forward, we can come backward as well. We can start our journey from this point, vertex A, we can start our journey from vertex B as well. If I just move from vertex A to vertex B with the iterative process, as I explained before, with the Bellman's principle of optimality, at individual stage we will take the decision and we will reach to the ultimate stage to address the whole problem. Now, that recursive relation is that process is the forward recursive process. We can go backward as well, that is starting from vertex B to vertex A. That is why let me first divide the problem into different stage. You see, we can name this stage as stage 0. The next stage where only the nodes 8 and 9 are there, stage 1. This is stage 2. This is stage 3. This is stage 4. Just divide, if I just divide the whole problem into these different stages, then first there is nothing to decide at stage 0, we will just move from 10 to the 8 or 9 because we wanted to go backward. In stage 1 we have to just take a decision whether to choose 8 or 9. From the figure it is very clear that is 3, that is why we will select the point 8. Once we have reached to 8, we need not to consider anything about the previous stage. We are happy with this decision, we have this optimal value only is needed for the next. We will move to the next stage, stage 2. If I move to next stage 2, if you see, if I just associate a state variable, as I say that for each stage there is a state variable. That is why state variable can be either 5 or 6 or 7. Thus, the state variable can take any value of these 3, but which one to select? For that thing we have to select the return from the previous stage only. That part let me just elaborate in the next. Once we are in the stage 0, that means we are at vertex 10. Here let me put n is equal to 0 and the state variable s is equal to 10. When n is equal to 1, then state variable could be either 8 or 9 as we have seen, and let us see the corresponding objective functional value at different alternative, because we are moving in a discrete decision space. Here we have only 2 alternatives with us, either 8 or 9. That is why we can take a decision here. We can formulate this is the naming convention. We can formulate this objective functional value. That means we will consider f18, that is from 10 to 8 this is coming 8, and f19, that is the root 9 to 10, this is 4, and from here certainly we will select 3, that is my optimal value. If I move to the next, that means we are moving to n is equal to 2. How many alternatives we had? We had 5, 6 or 7. These are the alternatives. Here just wanted to mention you one thing, that for taking decision I have used the transformation equation like that f1, let me put it S1, this is S0, this is S2, f1 S1 is equal to This is the minimization problem. We wanted to minimize the objective function f1 s1 is equal to minimum of RD1 plus previous stage, that is f0 10 rather s1 s0 rather, alright. If this is so, then we have two alternatives with us. One is RD1 is 3 plus 0, this is 0 always, and this is 4 plus 0. That is why we have selected the 3 value here. Here let us see how many alternatives we are having. We are having only 4 alternatives, 5 to 8, 6 to 8, 6 to 9, 7 to 9. Alright. If we have these alternatives with us, let us see, let us formulate the function here as well. 5 to 8 means we have considered once we are reaching to point 8, the value was 3, and at 5 it was 7. That is why it is 7 plus 3, this is equal to 10 units, say 10 rupees or 10 units of rupees we have to consider. If I move to 6 to 8, again up to come, if I just move to 6 to 8, the immediate cost I have to incur 3, and what about the previous one, that is coming again 3, because at point 8 it was 3, that is why we are getting equal to 3 plus 3 6. For 6 to 9, previous stage the optimal value is 3, always it is, if I just write down the equation, it is f2 s2 is equal to minimization of RD2, that means the decision, if I consider either this or D2 can take either this value, these are the 4 alternatives it has, f1 s1, f1 s1 we have already got 3, that is why we have, these are the values for us, and this is 4 plus 3 is equal to 7. Then certainly this is optimal for us, 6 is the optimal at this stage. Thus, if I just look back the table, once we are reaching to stage 2, optimal solution we got, that is 6. We need not to, once we are moving to stage 2 to stage 3, we need not to consider that how we have reached to stage 2, where the optimality occurs, it is not important for us. Only important thing is that how much optimality we have achieved here. That is why if I just write down the whole detail in the next, then I can write down in a table in this manner. Just let me read this table properly. I have written the alternatives 5, 6, 7, that is for stage 2 here. These are the headings for it: initial state, the decisions, immediate cost we have to incur for that decision, and what is the resulting state, what was the optimal return in the previous stage, and the functional value, accordingly we will take the decision, that is the thing. At point 5, 5, 8, whatever I said, same thing I have written here, and if I consider the optimization problem up to this point, then this could be the individual optimal solution for each state values. Let me move to the next, where the another 3, 2, 3, 4, that is stage 3 is there, 2, 3, 4. If I just write down the same information, same kind of information here, we could see that from 2 there are only 2 alternatives, 2 to 5, 2 to 6. This is the immediate cost, this is the resulting state, this is the optimal solution for the previous stage, because just now we have considered for the 5 it is 10, that is why we written 10, and therefore the total cost 10 plus 10 20. 3 to 6, once we are reaching to 6, how much I have to immediate cost I have to incur, that is 6, and for 6 this is the 6 is the optimal solution, we have written 6. How we have reached to 6, that is not important for us, as I said again and again, and this is for 3 to 7, for 7 the optimal is 8, in that way we have written 8 plus 8 is equal to 16, and among these 3 12 is the minimum one, that is why this is the optimal solution at this stage. Let me move to the next, and if I
just reach to 0.4, then this is again the same thing we have written, the at 0.4 the optimal value is 15, but if I consider the whole together 2, 3, 4, that is stage 3 together, then the optimal value is 12, either coming from this point or this point, any one of these two. Alright, let me move to the next, that is stage 4, only one, that is the whole problem. There are two alternatives, 1 to 2 and 1 to 3 alternatives, 1 to 2, 1 to 3 and 1 to 4. For 1 to 2 we are incurring 14 units. Similarly, for 1 to 4 also we will incur the same 14 units. Thus, we can say the optimal solution is, for this problem the optimal solution, rather the minimum cost policy we can write down in this way. Either we have done, this is one alternative with 14 units, we have to just bear the cost, and this is coming 1 to 2, 14. If we go back, then it was 12, all right, and this is the 12 is the, yeah, this is 2, this is 12, this is, sorry, this is 2, 12. Now, this 12 we are getting from 2, if I go to 2, this 12 we are getting here, that means go to 6. For 6 we are getting 6 here, 6 to 8. In this way we can get the whole path, and this is the path for us, 1 to 6 to 8 to 10. There is another alternative path is also there, we can move 1 to 4 to 6 to 8 to 10. For both the cases we need to incur 14 units. And that is the optimal solution as a whole for this problem. Now, that is all about the dynamic programming problem. Now, I can give you another problem for practice. This is a nice problem, you can work on it, and there is a hint also how to consider the state variable and state variable. We have considered 6 stages and there are few state variables we have considered. And this is the problem, you can work it and you can get the optimal solution in the similar manner. And this is the multi-stage decision process. We have considered the decision space as a discrete one. That is why there is a need to discuss further how to consider the uncertainty in the whole decision process. This is one part we should consider in the multi-stage thing, the multi-stage decision process, that is dynamic programming, and another topic we have to address, that is the dynamic programming problem where the state variables will move in the continuous space. That is all for today. Thank you very much.